excuse me. I hope, let me double check everything here. V in minus 0 divided by R, 0 minus VO divided by XC, 1 over yeah, so XC multiplied by V in, and XC is 1 over SC. It looks correct. I hope I didn't make any mistakes. Okay, so so this circuit is the integrator. When you only have an RC circuit here with an op-amp, the capacitor is in the feedback. Okay, that becomes integrator. Now, let me erase this one. Another circuit that I want to show you. Promise you this is the last circuit. So I'm just gonna switch these two elements. Let's have this one C, this one R. So again, an RC circuit, but this time the resistance or the resistor is in the feedback. Okay, again, I'm gonna write KCL at this point. V in minus 0 divided by XC is equal to 0 minus VO divided by R. So this time it means that VO divided by R is equal to negative of V in divided by XC. Okay, yeah, looks okay. So it means that VO is equal to negative of R over XC times V in. What is XC? XC is equal to 1 over SC. So let's replace this here. It means that VO is equal to 1 over SC. It comes to the numerator, so it becomes negative RC. Let me write it again like this, times SV in. So this is how output voltage and input voltage are related in this configuration. Again, if I take inverse Laplace transform of this one, this is in S domain. If I take Laplace transform of this one, it means VO of t is equal to negative RC times, this is derivative, right? Times dVO, this is lowercase dVO of, this is basically what we end up with. I hope I didn't make any mistakes in these coefficients. I think I'm okay. Excuse me. So as I think you've guessed so far, this circuit, it's called differentiator. Okay. So 6 circuits I showed you in these series of videos so far. 4 of which you had seen before. The other 2, I think they were new. I'm not sure if you saw this in your electronics course or in your other courses, but these are the 6 circuits that I just talked about. Inverting amplifier, non-inverting amplifier, subtractor, adder, integrator, and excuse me, and differentiator. Okay, so now let's go back to feedback control that you saw before. Let's say we want to implement feedback control for a system, and we want to use PID. This is the transfer function of our plant. This is our output. Let's say we don't have any sensor. Okay, so this is our ref. Right, and if you remember, this one is the error. So the first part that we have to implement is this part. We just have to subtract two signals, this signal and this signal. How can we do that? We have a circuit that does that for us, and a subtractor. Okay, so this circuit can basically, like if we have something like this, positive, negative, this is Vref. Maybe I should do this. It doesn't matter, but just gonna be easier for me to do it like this way. And this is output voltage, and this is R. If we keep all these resistors the same, this is gonna be Vref minus VO. Okay, now the main part of the lecture here, how to implement PID control. So if you remember, PID has three terms: proportional, integral, and derivative. So let's say Kp, Ki, and Kd. Okay, so we have like all of these, right? We have all of these. We know how to multiply a signal, how to amplify a signal. So this is going to be an amplification. This is going to be taking integral of the signal. This is going to be to differentiate the signal, to take the derivative of the signal. Okay, so what we basically do here, let me take this one here. This one here. So we basically want to multiply the error by Kp, then plus Ki over S plus Kd times S, right? So let's just like do these terms separately first. So remember that the integral and integrator and differentiator take the integral and derivative of a signal, but it has a negative coefficient, right? Because it has a negative coefficient, I'm gonna use an inverting amplifier for this one to have like all of them with negative